क्याप थ्योरम पुग्नु भएको त linearizability here means that there's only one copy of the data and all operations are atomic. This guarantees consistency even though there exist many replicas in a distributed system. Writes and reads are taking place concurrently. The reads from a different node follower can followers can be different होइन. For example, मैले मेरो साथीले गुगल सर्च गर्दाखेरि मेरोमा लेटेस्ट न्युज रिड भइसक्यो, साथीकोमा भएन किनकि साथीले डिफ्रेन्ट नोटबाट गरेको थियो। अनि त्यसपछि since we expect that नोटमा सबभन्दा लेटेस्ट न्युज एकैचोटि वर्क हुँदैन, त्यही हस्पिटलको लागि वर्क पर्छ। आवाज भन्नुको लागि लिनियर सिस्टम भयो भने बेस्ट हुन्छ। लिनियर सिस्टम पनि डिफ्रेन्ट टाइप्सको हुन्छ, सबैभन्दा बेस्ट भनेको लिनियर सिस्टम नै हो। अब लिनियरको कति लिनियर कति हुन्छ नि त, जस्तै उसको के अरे आइसोलेसनमा पनि रिड कमिटेड थियो, अनि स्न्यापसट आइसोलेसन थियो, अनि त्यसपछि त्योभन्दा बेटर चाहिँ उसलाई त्योभन्दा बेटर चाहिँ के हुन्थ्यो भने उसलाई सिरियलाइज गर्दाखेरि हुन्थ्यो। अनि यसमा चाहिँ पुरै सिरियली एक्जिक्युट गर्ने एउटा हुन्थ्यो, नत्र पनि अर्को टु फेज लकिङ भन्ने हुन्थ्यो एउटा। अनि त्यो पनि भएन नि, सिरियलाइजेबल स्न्यापसट आइसोलेसन भन्ने कुरा थियो हो। अब सिरियलाइज र लिनियराइज भनेको चाहिँ के हो? सिरियलाइज भनेको चाहिँ के हो भने कुनै पनि ट्रान्ज्याक्सन, सिरियलाइज चाहिँ ट्रान्ज्याक्सनमा रिलेटेड हो। टु अ ट्रान्ज्याक्सन, कुनै पनि ट्रान्ज्याक्सनमा एउटै कुरा एउटा अब्जेक्टलाई मल्टिपल ठाउँबाट रिड गर्दाखेरि एउटा अब्जेक्टलाई मल्टिपल ठाउँबाट रिड र राइट गर्दाखेरि चाहिँ हुने डिफरेन्सेसलाई चाहिँ सिरियलाइजेबिलिटीले हेल्प गर्छ। अब त्यसमा चाहिँ के भन्छ भने सिरियलले गर्न त एक्चुअल सिरियल एक्जिक्युसनलाई चाहिँ सिरियलले गर्न भन्नुहुन्छ। टु फेज लकिङले चाहिँ ऊ एक्सक्लुसिभ लक र सेयर्ड लकको कुरा गर्छ। सबैले रिड गर्दाखेरि चाहिँ सेयर्ड लक हुन्छ भने राइट गर्ने बित्तिकै त्यसले आफ्नो लकलाई एक्सक्लुसिभ पार्नुपर्छ। सिरियलाइजेबल स्न्यापसट आइसोलेसनमा चाहिँ एमबिसिसी भनेको मल्टी भर्जन कन्करेन्सी कन्ट्रोल भनेको कार्य मल्टिभर्जन कन्करेन्सी कन्ट्रोल होइन। यस, अनि यसमा चाहिँ अब कुन चाहिँ भर्जन स्टेल हो भन्दै हेर्छ, त्यस्तो हुन्छ। अब लिनियराइजेबल भनेको चाहिँ के हो भने दुईवटा डिफ्रेन्ट नोड्सबाट रिड गर्दा के अरे सिरियलाइजेबल भनेको चाहिँ एउटा अब्जेक्टलाई कुनै पनि एउटा ट्रान्ज्याक्सनको एउटा अब्जेक्टलाई रिड गर्दाखेरि हुने डिफ्रेन्सेस। लिनियराइजेबल भनेको चाहिँ कुनै पनि दुईवटा डिफ्रेन्ट नोड्स अथवा डिफ्रेन्ट फलोवर्सबाट रिड गर्दाखेरि हुने डिफ्रेन्सेस। अब लिनियराइजेबल चाहिँ के भन्छ भने कुनै पनि अब्जेक्टबाट कुनै पनि फलोवरबाट रिड गर्दाखेरि चाहिँ त्यहाँनिर हुनु हुँदैन, के भन्छ डिफ्रेन्सेस देखिनु हुँदैन। जस्तै मैले एक ठाउँबाट रिड गरेर मेरो साथीले एक ठाउँबाट रिड गरेँ भने दुईवटामा डिफ्रेन्स हुनु भएन। अब त्यो डिफ्रेन्स कसरी नदेखाउनु त? अब त्यसको लागि के गर्न सकिन्छ भने लिनियराइजेबल बनाउनलाई के गर्न सकिन्छ भने जब कुनै पनि टाइममा जस्तै दुईटा क्लाइन्टले एउटा लिडर अथवा फलोअरबाट रिड अथवा राइट गर्दैछ, एउटा क्लाइन्टले रिड गर्दैछ, त्यतिखेर इनिसियल भ्यालु जे छ त्यही आउने भयो। अब उसले रिड गर्दै गर्दाखेरि अर्को क्लाइन्टले त्यहाँनिर भ्यालु एउटा राइट गर्यो, अनि त्यसपछि अर्को मान्छेले अब यही क्लाइन्टले हुन्छ अथवा कुनै अर्को क्लाइन्टले फेरि भ्यालुलाई रिड गर्यो भने यो चेन्जेस कतिखेर देखाउने? यो त भएको छैन। अब यहीँनिर अर्को कुनैले पनि यसले पनि एकचोटि रिड गरेको अथवा राइट गरेको छैन, त्यसलाई कसरी देखाउने भन्ने कुरा हुन्छ। अनि अब यो हुँदाखेरि चाहिँ कन्करेन्टली रिड र राइट गर्दाखेरि भ्याल्युज नन डिटर्मिनिस्टिक हुन्छ। So the read can hop from new value to old one, होइन? त्यो हो। अब लिनियराइजेबल बनाउनलाई चाहिँ के गर्नु पर्यो? टु मेक सिस्टम लिनियराइजेबल, टु मेक अ सिस्टम लिनियराइजेबल, need to add another constraint. के हो त्यो constraint बुझौँ है त। Shit, यता छ म पढ्दैछु त यार। अब in a linearizable system, we imagine that there must be some point in time between the start and end of a write operation at which the value x atomically flips from 0 to 1. Okay, thus, if one client's read returns the new value 1, all subsequent reads must also return the new value, even if the write operation has not yet been completed. You बुझ्दै भयो। This timing dependency is illustrated with an arrow in figure 9.3 रे। यहाँनिर के भएको छ भने फर्स्टमा रिड गर्दा इनिसियल भ्यालु 0, यहाँ पनि रिड गर्दा इनिसियल भ्यालु 0, कन्करेन्टली राइट हुन थाल्यो। यो पोइन्टमा एउटा रिड क्लाइन्टको रिडले 1 पायो भने यसपछि हुने सबै रिडको भ्यालु 1 हुनु पर्यो। त्यो बुझ्यो। Even though this is continuing नि त हैन, यो हुँदा हुँदै पनि सबै हुनु पर्यो। We can further refine this diagram to visualize each operation taking an effect atomically at some point in time. A more complex example is shown in figure 9.4. In 9.4, we add a third type of operation besides read and write. यो भनेको चाहिँ compare and set. This means the client requested an atomic compare and set operation. If the current value of register x equals v old, it should atomically be set to v new. If x is not equal to v old, then the operation should leave the register unchanged and return an error. R is the database's response. अब कम्पेयर गर्छ, ओल्ड भ्यालुसँग म्याच छ भने न्यू भ्यालु गर्छ, अनि न्यू भ्यालु छ भने त्यसलाई अनचेन्ज छोडिदिन्छ। यो भनेको चाहिँ कम्पेयर एन्ड सेटको कुरा हो। Each operation in figure 9.4 is marked with a vertical line inside the bar for each operation at the time when we think the operation was executed. Those markers are joined up in a sequential order, and the result must be a valid sequence of reads and writes. Okay, those markers are joined up in a sequential order, and the result must be a valid sequence of reads and writes. And the result must be a valid sequence of reads and writes for a register. Every read must return the value set by the most recent write. So every read must return the value set by the most recent write. Okay. The requirement of linearizability is that the lines joining up the operation markers always move forward in time from left to right, never backward. This requirement ensures that the recency guarantee we discussed earlier, once a new value has been written or read, all subsequent reads. Definition. अब यहाँनिर के हुन्छ भने जहिले पनि sequentially अगाडि बढ्नु पर्यो. There are a few interesting details to point out in figure 9.4. First, the client B sends a request to read X. Then client D sends a request to set X to 0. First client B sends त्यसपछि D लाई X 0 बनाउनु भनेर भन्छ. Nevertheless, the value returned to B's read is 1. किनकि फर्स्टमा डीले एक्सको भ्यालु 0 गर्नु पर्यो, अनि त्यसपछि एले एक्सको भ्यालु 1 गर्नु पर्यो, अनि त्यसपछि फाइनली बीले रिड गर्यो. Although this is not the order in which the requests were sent, it is an acceptable order because the three requests are concurrent. एकैचोटि भएको छ. Perhaps B read request was slightly delayed in the network, so it only reached the database after the two writes. Okay. Client B's read returned 1 before client A received its response. B को B ले 1. Okay. Response from the database saying that the write of value 1 was successful. This is also okay because it does not mean that the value was read before it was written. It just means that the okay response from the database to client A was slightly delayed in the network. This model does not assume any transaction isolation. कुनै पनि transaction isolation assume गर्दैन. त्यो भनेको चाहिँ कस्तो भने A लाई रिड गर्दै गर्दाखेरि एउटै अब्जेक्टलाई दुईटा डिफरेन्ट ठाउँबाट कसैले पनि राइट गर्दाखेरि कन्करेन्टली राइट गर्न नमिल्लोस्. त्यही कुरा हो ट्रान्जेक्सन आइसोलेसन भनेको. And the client may change the value at any time. For example, C first reads 1 and then reads 2. C first reads 1 and then reads 2 because the value was changed by B between two reads. किनकि the value was changed by B between two reads. So first read मा 1 थियो जुन चाहिँ A को भ्यालु थियो, A को A ले सेट गरेको भ्यालु थियो, त्यसपछिको रिडमा चाहिँ 2 आयो किनकि क्लाइन्ट B ले त्यसलाई फेरि कम्पेरेन्ट सेट गरेर चेन्ज गरेको थियो. An atomic compare and set operation can be used to check the value hasn't been concurrently changed by another client. B and C's CAS requests succeed, but these CAS request fails. By the time database processes it, the value of X is no longer. B र C को compare and set request सक्सेस हुन्छ, तर D को चाहिँ फेल हुन्छ. किन फेल हुन्छ भनेर हेरौँ है त. त्यसपछि यसले रिड गर्यो, भ्यालु त 4 आउनु पर्ने, यहाँ किन एरर आयो. अब त्यो हेरौँ. An atomic compare and set operation can be used to check the value hasn't been concurrently changed by another client. B and CS request succeed, but D CS request fails. By the time data is processed, the value of X is no longer 0. The final read by client B in the setted bar is not linearizable. The operation is concurrent with C's CS right. Which updates X from 2 to 4. In the absence of other requests, it will be okay for bees to return, read, read, read to read, carry. In the absence of other request, the final equal line B in the sidebar is not linearizable. The operation is concurrent with CCAS, right, which updates X from 2 to 4. In the absence of other request, it would be okay for B's read to return 2. However, client A has already read the new value before B's read started. Mhm. So B is not allowed to read any older value than A. Again, the same situation already is. ए किन चाहिँ भनेको छैन नि त है. Again, the same situation. This is the intuition behind linearizability. The formal definition describes it more precisely. It is possible, though computationally expensive, to test whether a system behavior is linearizable by recording the timings of all requests and responses and checking whether they can be arranged in the valid sequential order. Linearizable can be easily confused with serializability, as both words seem to be something like it can be arranged in sequential order. However, they are two quite different guarantees, and it is important to distinguish between them both. Serializability is an isolation property of transactions, so where every transaction may read and write multiple objects, raw documents, or records, होइन, write multiple objects अथवा सिंगल अब्जेक्ट पनि त हो नि त. It guarantees that transactions behave the same as if they had executed in some serial order, each transaction running to completion before the next transaction starts. It is okay for that serial order to be different from the order in which transactions were actually run. Linearizability is a recency guarantee on reads and writes of a register. Linearizability is a recency guarantee on reads and writes of a register in an individual object. You see, it is a recency guarantee of reads and writes of a register an individual object. It does not group operations together into transactions like with a serializable and other stuff. So it does not prevent problems such as write skew unless you take additional measures such as materializing conflicts into the bootstrap. Database may provide both serializability and linearizability. This combination is known as strict serializability or strong one copy serializability. strong answer. Implementation of serializability based on two-phase locking or actual serial locking are typically linearizable. However, serializable snapshot isolation is not linearizable by design because it makes read from consistent snapshot to avoid contention between readers and writers. The whole point of consistent snapshot is that it does not include writes that are more recent than the snapshot, and thus reads from snapshot are not linearizable. मैले यो कुरा चाहिँ बुझिनँ compare the value with if yes to question answer question answer what circumstances is generalizability useful in? Being the final score of a sporting match is perhaps the frivolous example. The result that is outdated by a few seconds is unlikely to cause any alarm in this situation. However, there are few areas in which reliability is an important requirement for making a system work correctly. Locking in leader election. A system that uses single leader replication needs to ensure that there is needed only one leader, not several. One way of electing a leader one way of electing a leader is to use a lock. Every node that starts up tries to acquire the lock, and the one that succeeds becomes the leader. No matter how this lock is implemented, it must be linearizable. That is, all nodes must agree on which nodes owns the lock. Otherwise, it is useless. Coordination services like Apache Zookeeper and etcd are often used to implement distributed locks and leader election. They use consensus algorithms to implement linearizable operation in a fault-tolerant way. They use consensus algorithms to implement linearizable operation in a fault-tolerant way. We discussed that there are still many subtle details to implementing locks and leader election correctly. See for the example in fencing shoot the leader and the lock, and libraries like Apache Curator. 9.4. However, linearized storage service is the basic foundation of a task. There are still many subtle details to implementing logs in live election correctly. See, for example, fencing in and store locking is also used at much more granular level in some listed databases or Oracle data application clusters. When we use log for disk space with multiple nodes sharing access to the same disk storage system, since these neural logs are on the crucial path of transaction execution. RSC deployments usually have a dedicated cluster interconnect network for communication between database nodes. क्वेसन नम्बर 5 मात्रै बाँकी रह्यो। मेरो क्वेसन नम्बर 5 चाहिँ के भन्छ भने लिनियराइजेबिलिटीको डेफिनेसन चाहिँ के भन्छ भने लिनियर ग्यारेन्टी अफ रिजन राइट ह्यापनिङ इन अ रजिस्टर विच मिन्स कुनै एउटा अब्जेक्टमा मात्रै यो अन्डरस्ट्यान्डेबल पनि छ अलिअलि तर छैन पनि। अन्डरस्ट्यान्डेबल कुन सेन्समा छ भने दुईटा डिफ्रेन्ट रेप्लिकाले एउटै डकुमेन्ट एउटै उसमा रोमा रो पनि के भन्नु रजिस्टरमा एउटै रजिस्टरमा रिड्स अर राइट गर्दाखेरि डिफ्रेन्ट हुनु र एउटा रेप्लिकामा हुनु कस्तो कुरा गर्न खोजेको होला। अनि अल्सो इफ टु नोड्स आर ट्राइङ टु रिड द सेम डकुमेन्ट जस्तै सिरियलाइजेबिलिटी हुन्छ वाट डिटरमाइन्स कि यो लिनियराइजको प्रब्लम हो कि सिरियलाइजको प्रब्लम हो। आई मिन what determines that it is a register that has been in the doc किनकि केले डिटर्माइन गर्छ कि एउटा कुनै ट्रान्ज्याक्सन हो कि होइन, धेरैवटा कुरासँग प्याक भएकै हुनुपर्छ भन्ने छ कि। जस्तै ट्रान्ज्याक्सन भनेको मल्टिपल अपरेसन्सहरू एकै ठाउँमा एकुमुलेट गरेर हुनु हो होइन। अब सपोज सिरियलाइजेबल हुनुलाई ट्रान्ज्याक्सन हुनैपर्छ, ट्रान्ज्याक्सन हुनैपर्छ भने पनि एउटै 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 रेप्लिकामा अथवा एउटै क्लाइन्टले गरेको क्लाइन्टले एउटै पर्छ। ए पछि पढौँ है, क्वेसन नम्बर 5 बाँकी छ। अब relying on linearizability भन्छ। In what circumstances linearizability is useful? यो त थाहा छ, सबैभन्दा इक्जाम्पल भनेको त्यो फुटबल। अर्को अब फुटबलको त्यो स्कोर हेर्ने, अब यो चाहिँ त्यति साह्रो हार्मफुल नभए पनि अरू खतरा कुराहरू छ अरे। एउटा भनेको लकिङ एन्ड लिडर इलेक्सन, इन विच अब यसमा चाहिँ के हुनुपर्छ भने कुनै पनि के अरे सिस्टम जसमा एउटा लिडरले मनपर्छ फलोअरलाई आफ्नो रेप्लिका गराउँछ भने त्यसमा लिडरको छान्नको लागि त्यसमा लिडरलाई इलेक्ट गराउनुपर्छ। अनि त्यसमा चाहिँ फेन्सिङ भन्ने एउटा फेन्सिङ इस्यु भन्ने हुन्छ, जसमा चाहिँ एउटा कुनै पनि लिडर छ अनि उसले ऊ अनलाइन छ तर बिचमा केही गार्बेज कलेक्सन गर्दा अथवा केही भएर ऊ सम टाइमको लागि अफलाइन गयो अनि त्यसपछि फर्केर आउँदाखेरि आफ्नो अपरेसन जस्तै कन्टिन्यू गर्न खोज्छ। तिनीहरूलाई थाहा हुँदैन ऊ अफलाइन भएर अरू सबै नोट्सले फलोअर डेट भइसक्यो भनेर उसलाई मारिदिइसके। अनि अब नयाँ लिडर पनि आइसक्यो, अनि त्यहाँनिर हल्का त्यसको स्प्लिट ब्रेन हुनसक्छ होइन। त्यसैले त्यो कुरालाई चाहिँ अब लिडर अब लक राखिदिन्छ, हरेक लिडरसँग एकपल्ट लक हुन्छ, त्यो चाहिँ इन्क्रिमेन्ट हुन्छ लिनियरली। अनि अब उसले कुनै काम गर्न खोज्दाखेरि उसले आफ्नो लक प्रोभाइड गर्छ, लक त पुरानो हुन्छ, पुरानो भएपछि उसलाई दिँदैन, त्यस्तो गर्छ क्यारे लिडर लकमा। अनि यो चाहिँ धेरैवटा कुराहरू जस्तै जुकिपरहरू के हुन्छ भनेर भन्छ। डिस्ट्रिब्युटर लकिङ इज अल्सो युज, डिस्ट्रिब्युटर लकिङ पनि युज हुन्छ भन्नुहुन्छ, यसको बारेमा भनेको छैन त्यसमा पढ्दैन। Constraint and uniqueness criteria. Uniqueness constraints are common in database. For example, a username or email address must uniquely identify one user. In a file storage service, there cannot be two files with the same path and file name. Oh. If you want to enforce this constraint as the data is written, such that if two people try to concurrently create a user or a file with the same name, one of them will be returned with an error. You need linearizability. Oh, good example. This situation is actually similar to a lock. When a user registers for your service, you can think of them acquiring a lock on their chosen username. The operation is also very similar to an atomic compare and set, setting the username to the ID of user. Claim it. Care. The operation is also very similar to an atomic compare and set. The operation is also very similar to an atomic compare and set, setting the username to the ID of the user. Setting the username to the ID of a user who claimed it, provided that username is original. Compare गर्छ यो username छ कि छैन भनेर, छैन भने set गर्छ, बुझ्यो। Similar issue arise if you want to ensure that bank account balance never goes negative. Similar issue arise if you want to ensure that a bank account balance never goes negative, or that you don't sell more items than you have in stock in the warehouse, or that two people don't concurrently book the same seat on a flight or in a theater. These constraints all require there to be a single up-to-date value, the account balance, the stock level, the seat occupancy, that all nodes agree on. अब यसलाई लिनियराइजेबिलिटी चाहिन्छ भने अस्ति नै हामीले पढेको to make sure that two users concurrently do not book the same same row we need linearizability. What about in real applications, it is sometimes acceptable to treat such constraint loosely. For example, if a flight is booked, you can move customers to a different flight, offer them compensation for the inconvenience. In such cases, linearizability may not be needed, and we'll discuss how to interpret the constraint in timeliness and integrity. However, a a hard unique constraint such as the one you typically find in relational database, requires linearizability. Other kinds of constraints, such as foreign key or attribute constraints, can be implemented without requiring linearizability. Uh, Cross-channel timing dependencies. Notice a detail in figure 9.1. If Alice hadn't exclaimed the score, select abstract from final score, Bob wouldn't have known that the result could be still. He would have just refreshed the page again a few seconds later and to see the final score. The linearizability violation was only noticed because there was an additional communication uh, channel in the system, Alice voice to Bob ears. The similar situation can arise in computer system. For example, you have a website where users can upload a photo and a background process resize the photo to a lower resolution for faster download thumbnails. The architecture and data flow of the system is illustrated in figure 9.5. Here, you have a photo and the background process resize the photo to a low resolution for faster download. The architecture and the upload image web server stores full time file storage. Sends message, telling message. The image resizer needs to be explicitly instructed to perform a resizing job. And this happens, and this instruction is sent from the web server to the resizer via a message queue. The web server does not place the entire photo on the queue. Since most message brokers are designed for small messages and a photo may be several megabytes in size, instead, the photo is written to a file storage device, and once the write is complete, the instruction to the resizer is placed on the queue. Get it? The image resizer needs to be explicitly instructed to perform a resizing job, and this instruction is sent from the web server to the resizer via message queue. The web server does not place the entire photo on the queue since most message brokers are designed for small messages. Right? and a photo may be several megabytes in size. Instead, the photo is written to a file storage service, and once the write is complete, the instruction to the resizer is placed on the queue. Mm. If the file storage service is linearizable, then the system would work fine. If it is not linearizable, then there is a risk of rest conditions. The message queue, step 3 and 4 in figure 9.5, mm, might be faster than the internal replication inside the maybe faster than the internal replication inside the storage device. In this case, when the resizer fetches the image, step 5, it might see an old version of the image or nothing at all. If it processes an old version of the image, the full size in the resized image in the file storage becomes permanently inconsistent. This problem arises because there are two different communication channels between web server and the resizer, the file storage and the message queue. Without the recency guarantee of linearizability, the rest condition between these two channels are possible. This situation is analogous to figure 9.1, where there is also rest condition between two communication channels, that is depth replication in the real life order between Ali Smith and Bob's. Linearizability is not the only of meeting this race condition, but it is the simplest to understand. If you control the additional communication channel, like in the case of message queue, but not in the case of Alice and Bob, you can use an alternative approach similar to what we did discussed in reading your own rights and positions at the cost of additional complexity. Now that we've looked at a few examples in which linearizability is useful, let's think about how we might implement a system that offers linearizable semantics. Since linearizability essentially means behave as though there is only a single copy of the data, as though there is only a single copy of the data and all operations are on it are atomic. The simplest answer would be to really use a single copy of the data. However, that approach would not be able to tolerate false if the nodes holding that one copy if the node holding that one copy failed, that data will be lost or at least inaccessible until the node was brought up again. The most common approach to making a system fault tolerant is to use replication. Let's revisit the replication method from chapter 5 and compare whether they can be made linearizable. Single leader replication, potentially linearizable. In the system with a single leader replication, the leader has the primary copy of the data that is used for writes, and the followers maintain backup copies of the data on other nodes. If you make reads from the leader or from synchronously updated followers, if you make reads from leader or from synchronously updated followers, they have potential to be linearizable. However, not every single leader database is actually linearizable, either by design because it uses snapshot isolation or by concurrency box. Using the leader for read relies on the assumption that you know for sure who the leader is. As discussed in the truth is defined by the majority on page 300, it is quite possible for a node to think that it is a leader, when in fact it is not. And if the delusional leader continues to solve requests, it is likely to violate linearizability. With asynchronous replication, failover may even lose committed rights, mm, which violates both durability and linearizability. Consensus algorithm, linearizable. Some consensus algorithms, which we'll discuss later in this chapter, bear a resemblance to single-leader replication. However, consensus protocol contain measures to prevent split brain and stale replicas. Thanks to these details, consensus algorithms can implement linearizability storage safely. This is how Zookeeper and etcd works, for example. Multi-layer replication. Systems with multi-layer replication are generally not linearizable because they concurrently process writes on multiple nodes and asynchronously replicate them to other nodes. For this reason, they can produce conflicting writes so that require resolution. Such conflicts are an artifact of the lack of single copy of the data. Tedious replication probably not necessary for systems with linear replication dynamic style. People sometimes claim that you can obtain strong consistency by requiring the quorums, reads and write deliverables are is greater than 1. Depending on the exact configuration of the quorums and depending on how we define strong consistency, this is not quite true. Last write wins conflict resolution methods based on time of delay clocks. Resolution method based on time of day clocks in Cassandra are almost certainly non-result because clock time steps can be guaranteed to be consistent without an actual order due to clock skew. Sloppy columns also ruin any chance of reliability. Even with strict columns, non-reliability is possible as demonstrated in the next section. Intuitively, it seems that as the strict columns reason light should be linearizable in a dynamic style model. However, we have variable network delay. It is possible to have a race condition as demonstrated in figure 9.6 and writer set x equal to 1. Okay, okay. However, when I get 1 by however, 2 to 0 by Westland, 0 by 0 by the initial value of x is 0 and the writer and is obtaining x1 by sending the right to all three replicas n equal to 3 and w equal to 3. Concurrently, client reads from a quorum of nodes of two nodes r equal to 2 and sees a new value 1 on one of the nodes. Also concurrently, the right client b reads from different quorum of two nodes and gets back the value of 0 from both. The quorum condition is met. W plus r equal to n. But this execution is nevertheless not serializable. B's request begins after A's request completes. But B returns the old value. While A returns the new value, it is once again Alice and Bob switches to program. It is interestingly, it is possible to make dynamic style forums linearizable at the cost of reduced performance. A leader must perform repair synchronously before returning. A reader must perform repair synchronously before returning results to the application. And a writer must read the latest state of quorum of nodes before sending its right. However, React does not perform synchronous read repair due to the performance penalty. Cassandra does wait for a read repair to complete on the column list, but it loses linearity if there are multiple concurrent to the same key due to its use of last write in conflict resolution. Moreover, only linearizable read and write operation can be implemented in this way. A linearizable competent set operation cannot, because it requires consensus algorithm. Thus, in summary, it is safest to assume that a linear system with dynamic style application And some replication method can provide linear algebra in others cannot. It is interesting to explore the pros and cons of linear algebra in more depth. We already discussed some use cases of different replication method in chapter 5. For example, we saw that multi-threaded replication is often a good choice for multi-data center. An example of such deployment is listed here. Data center 1, data center 2, detail आफ्नो interest. Forcing a choice between linear changeability. Consider what happens if there is a network interruption between two data centers. Let's assume that the network within each data center is working and clients reach the data centers, but the data centers cannot connect to each other. With a multi-layer database, each data center can continue operating normally since writes from one data center are asynchronously replicated to other. All the writes are simply queued up and exchanged when network connectivity is restored. On the other hand, if a single leader replication is used, then the leader must be in one of the data centers. Any writes and any linearizable reads must be sent to the leaders. Thus, for any client connected to a follower data center, those reads and writes must be sent synchronously over the network to the leader data center. If the network between data center is interrupted in a single leader setup, clients connected to followers cannot contact the leader, so they cannot make any writes to the database nor any linearizable reads. They can still make reads from the follower, but they might be stale. If the application requires linearizable reads and writes, the network interruption causes the application to become unavailable in data centers. If the application requires linearizable reads and writes, the network interruption causes the application to become unavailable in the data centers that cannot contact the data. If the clients can connect directly to the leader data centers, this is not a problem since the application continues to work normally there. But clients that can only reach a follower data center will experience an outage until the network is repaired. The cap here. This this issue is not just a consequence of single leader and multi-leader application. Any linearizable database has this problem. No matter how it is implemented, the issue isn't specific to a multi-data center deployments. Isn't isn't specific to multi-center data deployments, but can occur on any unreliable network, even with one data center. The trade-off is as follows. If your application requires linearizability and some replicas requires linearizability, so disconnected from the other replicas due to a network problem, then some replicas cannot process request when they are disconnected. They must either wait until the network problem is fixed or return an error. Either way, it becomes unavailable. If your application does not require linearizability, then it can be written in a way that each replica can process requests independently, even if it is disconnected from replicas multi-layer state. In this case, application can remain available in the face of network problem, but its behavior is not linearizable. Thus, application that does not require linearizability can be more tolerant of network problems. This insight is popularly known as cap theorem. The cap theorem. This issue is not just consequence of single data and multi-layer replication. Any linearizable database has this problem. This issue is not just a consequence of single data and multi-layer replication. Any linearizable dataset has this problem, no matter how it is implemented. The issue is also not specific to multi-data center deployments, but can occur on any unreliable network, even with one data center. The trade-off is as follows. If your application requires linearizability, care trade-off. If linearizability is required, and some replicas are disconnected from other replicas due to a network problem, then some replicas cannot process requests while they are disconnected. They must either wait until the network problem is fixed or return an error. Linearizable one cap theorem. GA once thus application that does not require can be more tolerant of network problems. Although the trade-off has been known to design a database since the 1990s. CAP theorem was originally proposed as a rule of thumb without precise definitions, with the goal of starting a discussion about the trade-offs in databases. At the time, many distributed databases focused on providing linearizable semantics on a cluster of machines with CAP is sometimes presented as consistency, availability, or partition tolerance. Pick 2 out of 3. Unfortunately, putting it this way is misleading because network partitions are kind of a fault, so they aren't something about which you have a choice. They will happen whether you like it or not. At this time, when network is working correctly, a system can provide both consistency, linearizability, and total availability. When a network fault occurs, you have to choose between linearizability or total availability. Thus, a better way of phrasing CAP theorem would be either consistency or availability when partitioned, either consistent or available when partitioned. A more reliable network needs to make this choice less often, but at some point the choice is inevitable. In a discussion of in discussions of CAP theorem, there are several contradictory definitions of the term availability, and the formalization as theorem does not match its usual meaning. Many so-called highly available fault-tolerant systems actually do not meet CAP's idiosyncratic definition of availability. All in all, there is a lot of misunderstanding and confusion around CAP, and it does not help us understand the system better, so CAP is best avoided. The CAP theorem is formally defined and is a very narrow scope. It only considers one of one consistency model, linearizability, and one kind of fault, network partitions or nodes that are alive but disconnected from each other. It does not say anything about network delays, dead nodes, or other trade-offs. Thus, although CAP has been historically influential, it has later practical value for designing systems. There are many more interesting impossibility. यो यत्रो ठुलो पारेर झन् ए ला यसले त सकाइसकेछ त यार थाहा पाइनँ मैले क्याप थ्योरी तिमीहरूको पनि थियो होइन क्याप थ्योरी consistency, availability, and partition. Chartered accountant profession can सुन्नु हामी जान्छौँ बाहिर फोन पकाएर छैन है ब्रेक फेरि स्टार्ट गरिदिएँ मैले भाइ एकछिन चाहिँदैन There are many more interesting possibilities result in distributed systems, and CAP has now been superseded by more precise results, so it's mostly historical interest today. Linearizability and network delays. Although linearizability is a useful guarantee, surprisingly few systems are actually linearizable in practice. For example, even RAM on a modern multi-core CPU is not linearizable. If a thread running on one CPU core writes to a memory address and thread on another CPU core reads the same address shortly afterward, it is not guaranteed to read the value written by the first thread unless a memory barrier or fence is used. The reason for this behavior is that every CPU core has its own memory cache and store buffer. Memory access first goes to the cache by default, and any changes are asynchronously returned out to main memory. Since accessing data in the cache is much faster than going to main memory, this feature is essential for good performance on modern CPUs. However, there are now several copies of same data, one in the main memory and perhaps in several more various caches. These copies are asynchronously updated so linearizability is lost. Why make this trade-off? It also makes sense to use the gap theorem to justify the multiple memory core memory consistency model. Why make this trade-off? It makes no sense to use the gap theorem to justify the multi-core memory consistency model. Within one computer, we usually assume reliable communication. We don't expect one CPU core to be able to continue operating normally if it is disconnected from the rest of the computer. The reason for dropping linearizability is performance, not fault tolerance. The same is true for many distributed databases that choose not to provide linearizable guarantees. They do so primarily to increase performance, not so much for fault tolerance. Linearizability is slow, and this is true all the time, not only during a network fault. Can't we maybe find a more efficient implementation of linearizable storage? It seems the answer is no. Atya and Walsh prove that if you want linearizability, the response time of read and write request is least proportional to the uncertainty of delays in the network. Prove that if you want linearizability, the response time of read and write request is least proportional to the uncertainty of delays in the network. In a network with highly variable delays like most computer networks, timers and all, the response time of linearizable reads and writes is inevitably going to be high. A faster algorithm for linearizability does not exist, but weaker consistency models can be much faster. So this trade-off is important for latency-sensitive systems. In chapter 12, we'll discuss some approaches for avoiding linearizability without sacrificing correctness. Ordering guarantees. We said previously that a linearizable register behaves as if there is only one single copy of the data and that every operation appears to take effect atomically at one point in time. We previously said that a linearizable register behaves as if there is only one single copy of the data and that every operation appears to take effect atomically at one point in time. Mm. This definition implies that operations are executed in some well-defined order. We illustrated the ordering figure 9.5 by joining of operation in the order in which they seem to have executed. The line banaya, right? I hope so. Oh. Ordering has been a recurring theme in this book, which suggests that it might be an important fundamental idea. Let's briefly recap some of the other contexts in which we have discussed ordering. In chapter 5, we saw that main purpose of the leader in a single leader replication is to determine the order of writes in the replication log, that is, the order in which followers apply those write. If there is no single leader, conflicts can occur due to concurrent operations. Serializability, which we discussed in chapter 7, is about ensuring transactions behave as if they were executed in some sequential order. Transactions. Ensuring that transactions behave as if they were executed in some sequential order. It can be achieved by literally executing transaction in a serial order or by allowing concurrent execution while preventing serialization conflicts by locking or aborting. The use of timestamps and clocks in distributed systems that we discussed in chapter 8 is another attempt to introduce order into a disorderly world, for example, to determine which one of the two writes happened later. It turns out that there are deep connections between ordering, linearizability, and consensus. Although this notion is a bit more theoretical and abstract than the rest of this book, it will be helpful. It is very helpful for clarifying our understanding of what systems can and cannot do. We'll explore this topic in the next few sections. Ordering and casualty. There are several reasons why ordering keeps coming up, and one of the main reasons is that it helps to prevent casualty. We have already seen several examples over the course of this book where casualty has been important. Inconsistent prefix reads. We saw an example where the observer of a conversation first saw the answer to a question and then the question being answered. This is confusing because it violates the intuition of cause and effect. If a question is answered, then clearly the question had to be there first because the person giving the answer must have seen the question, assuming that they are not psychic and can see into the future. We say that there is a causal dependency between the question and the answer. A similar pattern appeared in figure 5.9, where you look at the replication between three leaders and notice that some writes could overtake others due to network delays. For the perspective of one of the replicas, it would look as though there was an update to a road that did not exist. Casualty here means that a row must be first created before it can be updated. यो त rights queue जस्तै भयो त. Client A inserts row to table on leader 1 and client B updates that row on leader 3. Insert value leader 1. Okay, and client B updates that row on leader 3. Update data set value plus 1 key equal to x. Value x1. However, leader 2 may receive carrot updates that row on leader 3 may receive the rights in a different order. Oh, there you go. It may first receive इसको update and then receive इसको write. Right? Consistent prefix reads. This guy now imagine the third person listening to the conversation through followers. He thinks it a mistake through a follower with a little lag. The things said by Mr. K go through a follower but with a little lag. The things said by Mr. Kunz have a longer replication lag. This observer would hear the follower Mr. K. However, Mr. Kunz. The observer looks at Mr. Cook is answering questions. Before Mr. Cook had even asked us, he probably but very confusing. In the technical concurrence, we observe that that two operations in B, there are three possibilities. Either A happened before we carry. In detecting concurrent threads on page 184, key ordering casualty. We have already seen several examples of where the score where casualty has been casualty. In detecting concurrent fact, we observe that if you have two operations A and B, there are three possibilities. Either A happened before B, or B happened before A, or A and B are concurrent. This happened before relationship is another expression of causality. If A happened before B, that means B might have known about A or built upon A or dependent on A. If A and B are concurrent, there is no causal link between them. In other words, we are sure that neither knew about each other. In the context of snapshot isolation for transactions, snapshot isolation and repeatability, we say that a transaction reads from a consistent snapshot. But what does consistent mean in this context? It means consistent with causality. If snapshot contains an answer, it must also contain the question being answered. Observing the entire database at a single point in time makes consistent with causality. The effects of all operations that happened casually before the point in times are visible. Observing the entire database at a single point in time makes it consistent with causality. That is, the effect of all operations that happened casually before that point in time are visible, but no operations that happened casually afterwards can be seen. Read skew, non-repeatable reads as illustrated in below, means reading data in a system that violates causality. Are examples of write skew between transactions, write skew and find also determine causal dependencies. Alice was allowed to go off call because through the transaction thought Bob was still on and vice versa. In this case, the action of going off call is causally dependent on the observation of who is currently on call. Serializable snapshot isolation detects write skew by tracking the causal dependency between transaction A. In the example of Alice and Bob watching football, the fact that Bob got a stale result from the server after hearing Alice exclaim the result is causality violation. Alice's exclamation is causally dependent on the announcement of the score. So Bob should also be able to see the score after hearing Alice. The same pattern appeared again in cross-channeling timing dependencies on Causality imposes an ordering on event. Cause comes before effect. A message is sent before the message is received. The question comes before the answer. And like in real life, one thing leads to another. One node reads some data and then writes something else as a result. Another node reads the thing that was written and writes something else in turn, and so on. The chains of causally dependent operation define the causal order in the system. That is, what happened before what. If a system obeys the ordering imposed by causality, we say that it is causally consistent. For example, cause and effect. For example, snapshot isolation provide causal consistency. When you read from the data, you see some piece of data, then you must able to see any data that causally precedes, assuming that it has not been deleted in the meantime. The causal order is not a total order. A total order allows any two elements to be compared. So if you have two elements, you can say always see which one is greater and which one is smaller. For example, natural numbers are totally ordered. If I give you any two numbers, say 5 and 13, you can tell me that 13 is greater than 5. However, mathematical sets are not totally ordered. That is A and B greater than B and C. Well, you can't really compare them because neither is a subset of other. We say they are incomparable, and therefore mathematical sets are partially ordered. In some cases, one set is greater than order if one set contains all the elements from another, but other cases they are incomparable. The difference between total order and partial order is reflected in different database consistency model linearizability. In a linearizable system, we have a total order of operations. If system behaves as if there is only a single copy of data, every operation is atomic. This means that for any two operations, we can always say that which happened first. Thus, ordering this total ordering is illustrated in timeline figure 9.4. Causality. We said that two operations are concurrent if we said that two operations are concurrent if neither happened before the other happens before concurrency. Put another way, two events are ordered if they are causally related. One happened before the other, but they are incomparable if they are concurrent. This means that causality defines a partial order, not total order. Some operations are ordered with respect to each other, but some are incomparable. Therefore, therefore, according to this definition, there are no concurrent operations in a linearizable data store. There must be a single timeline along which all operations are totally ordered. There might be several requests waiting to be handled, but the data store ensures that every request is handled atomically at a single point in time, acting on a single copy of data alongside a single timeline without any concurrency. Concurrency would mean that the timeline branches and merges again, and in this case, operations on a different branch are incomparable, that is concurrent. We saw this phenomenon on chapter 5, for example. Figure 5.14 is not a single straight line. To the order, but rather resembles different operations concurrently. The arrows in the diagram indicate causal dependency, the partial ordering of operations. If you are familiar with distributed version control systems such as Git, their version history are very much like the graph of causal dependency. Often one commit happens after another in a straight line, but sometimes you get branches when several people concurrently work on a project. And merges are created when those concurrent carry. Often one commit happens after another in a straight line, but sometimes you get branches when several people concurrently work on a project. Merges are created when those currently concurrently created commits are combined. Linearizability is stronger than causal consistency. So, what is the relationship between causal order and linearizability? The answer is linearizability implies causality. Get it? Any system that is linearizable will preserve causality correctly. In particular, if there are multiple communication channels in a system, such as the message queue and file storage service in figure 95, linearizability ensures that the causality is automatically preserved without system having to do anything special, such as passing around timestamps between different components. The fact that linearizability ensures causality is what makes linear system simple to understand and appealing. However, as discussed in the cost of linearizability, making a system linearizable can harm the performance and availability, especially if the system has significant network delays. For example, if it is geographically distributed. For this reason, some distributed data systems have abandoned linearizability, which allows them to achieve better performance but can make them difficult to work with. The good news is that a middle ground is possible. Linearizability is not the only way of preserving causality, there are other ways too. A system can be causally consistent without incurring the performance hit of making it linearizable. In particular, the cap theorem does not apply. In fact, causal consistency is the strongest possible consistency model that does not slow down due to network delays and remains available for the face of network failures. The good news is that a middle ground is possible. Linearizability is not the only way of preserving causality, there are other ways too. A system can be causally consistent without incurring the performance hit of making it linearizable. In particular, the cap theorem does not apply. In fact, causal consistency is the strongest possible consistency model that does not slow down due to network delays and remains available in the face of networking failure. And correct. In fact, the strongest possible consistency model that do not slow down due to network delays and remains available in the face of network failures. In many cases, systems that appear to require linearizability, in fact, only require causal consistency, which can be implemented more efficiently. Based on this observation, researchers are exploring new kinds of databases that preserve causality with performance and availability characteristics that are similar to those eventually consistent systems. As this research is quite recent, not much of it has yet made its way to the production system, and there are still challenges to be overcome. However, it is a promising direction for future systems. We won't go into all the nitty-gritty details of how non-linear system can maintain causal velocity here, but just briefly explore some of the key ideas here. In order to maintain causal consistency, maintain causality, you need to know which operations happen before which other operation. This is a partial order. Concurrent operation may be processed in any order. Concurrent operation may be processed in any order. But if one operation happened before another, then they must be processed in that order for every replica. Thus, when a replica processes an operation, it must ensure that all casually preceding operations, all operations that happened before, have already been processed. In some preceding operation, if some preceding operation is missing, the later operation must wait until the preceding operation has been processed. In order to determine causal dependency, we need somewhere describing the knowledge of a node in the system. If a node had already seen the value x when it issued the right y, then x and y may be causally related. The analysis uses this kind of question you would expect in a criminal investigation of fraud charges. Did the CEO know about the X at the time when they made the decision Y? The technique for determining which operation happened before which operation are similar to what we discussed in detecting concurrent writes. That section discussed causality in a leaderless disaster. यार यसले त मलाई उ गर्यो त उ चाहिँ त नानी त्यो के अरे what is consensus. RAM कति धेरै हो 360 मा छु 390 भनेपछि अलमोस्ट 400 सम्म पुग्नुपर्ने रहेछ अनि 40 पेज म 365 मा छु 365 मा छु अब मलाई पुग्नु 395 मा छु 30 पेज पन्ध्र मिनटको ब्रेक लिउँ ब्रेक आइदियो दस्तीहरू कति टाइम भयो? 50 51 10 मिनट 50 गुणा 10 मिनट nitty-gritty में जा देना तर दूसरे express the clear data. Now you need to know this operation happen when you need to this is a special order. Casual dependency capture करना हमने क्या आंसर we need know which operation happen when यो कुरा जान्छ we need somewhere describing the knowledge of a node in the system. We need to describe the knowledge of node in a system. Huh? If a node has already seen a value x issued when it issued the right y, then x may be causally related. X and y may be causally related. The analysts use this kind of question would expect a common invocation of fraud charges. Did the CEO know about the x at the time when they made the decision y? The technique for determining the operation happened before which operation are similar to what we discussed in this detecting concurrent writes. म एकचोटि यसलाई हेर्छु